Ladies and gentlemen, your class recording has begun. Yesterday, when you took the quiz on ionic bonding, there were a couple of general questions about ionic bonding. So, one of the questions said, why do atoms form bonds with one another? How did we answer that question? What did you put down as why atoms form bonds with one another? Christine, go ahead.
Because after they become like a cation or an anion, since one has a negative charge and one has a positive charge, they attract each other.
Okay, that would be more specifically the formation of an ionic bond, right? But why does that happen? Why do cations and anions form in the first place? Catherine, go ahead.
They want to get to a stable position, which is 8 valence electrons.
Stable, let's go, stable position or a stable configuration, which is 8 valence electrons. What other word we could probably throw in there, Catherine? What makes something stable? How do we know that this is a stable configuration, other than it has 8 valence electrons?
Low energy.
Low energy, right? That bonding happens to reach a low energy state, right? Christine, you kind of went over the ionic bonding idea, right? That an ionic bond is what? How would we describe an ionic bond?
Like, after the transfer of electrons and then the cation and the anion like bonding together.
So after we transfer electrons from one to the other, cation ends up with a positive charge, anion ends up with a negative charge, they attract, right? That's ionic bonding. Good there? Okay. Covalent bonding, we'll see, especially at the beginning, is almost exactly the same. For example, the first part of your outline today should look very similar to the previous outline because it's exactly the same. First, why do atoms form bonds? What's the purpose of bonding? Why do atoms bond? Or sorry, what is a bond first? What is a chemical bond? Trey, go ahead.
An attractive force that holds atoms together.
An attractive force that holds atoms together. You got it?
Yeah.
Okay. An attractive force that holds atoms together. Next, why do atoms bond? Trey, go ahead.
What was the question?
Why do atoms bond?
To get to a low energy
To
state.
get to a low energy state. The formation of chemical bonds involves energy. Bonds will form if atoms have a lower energy together than they did when they were separate. Bonds will form if atoms have a lower energy together than they did when they were separate. We have a name for this process of getting to a lower energy state. Trey, go ahead. Exothermic, right? Bond formation is generally an exothermic process, meaning that the products, the stuff we end up with, have less energy than the stuff we started with. That's going to be a key idea in the next unit when we talk about chemical reactions, this exothermic process, or giving off energy. We will definitely talk a lot about that in the next chapter on chemical reactions. Okay? Good there? And the way that this happens, the way that these elements go, or these atoms go about achieving low energy states is what? What equates to a low energy state for an atom? 8 valence electrons. Chemical bonds deal with valence electrons, right? Electrons in the highest energy level. And I added this part to the slideshow, but I forgot to put it into your outline. We talked about that 8 valence electrons is a low energy state. And we call that idea the octet rule. All right, all of that is exactly the same as when we talked about it in ionic bonding. Catherine, go ahead.
Isn't valence with an E?
the same as it was when we talked about ionic bonding. Christine, you told us before that ionic bonding involves what?
Cations.
And how do cations and anions form?
They transfer electrons.
That ionic bonding involves the transfer of electrons between atoms. But what we'll find, covalent bonding, right, that's not the case. So here's what I want you to do first. In the bottom left-hand corner of your outline, or the bottom right-hand corner of your outline, there's lots of space down there. I want you to draw for me the Lewis structure for chlorine. Draw me the Lewis structure for chlorine. Yes, Christine.
For the tests, are we going to get like a periodic table and stuff?
You will get a periodic table, the same periodic table that I've been giving you like on your other test, that green one that's laminated and stuff like that. So yeah, you'll have that periodic table. And you'll have it on your exam, on your midterm exam. All right. So here is the Lewis structure for chlorine. Questions? We good with this? 7 valence electrons, right? Each represented by a dot. Okay. Back in the first part of this unit, dealing with ionic bonding, or sorry, even before that. So, based on this Lewis structure, what is chlorine looking to do? Gain 1 electron, right? That'll get us to 8, okay? So, at the beginning part of this chapter, sodium came around, right? Sodium with its 1 valence electron. What is sodium looking to do with its 1 valence electron? Lose it, right? So this is a match made in heaven, yes? Right? Sodium's looking to give up 1 electron. Chlorine is looking to gain 1 electron. Sodium gives that electron away. Chlorine takes it on. Yay, everybody's happy, right? But now one's positive, one's negative. They attract each other. That's the bond. Okay? However, the story changes now, right? There's no sodium around. The only thing that's around is another chlorine. And this chlorine, just like the previous chlorine, right? 7 valence electrons. There we go. Right? So this is one big group. We'll make that into a big group like this. Okay, so the original chlorine that we drew is desperate for another electron. Being that it has 7 valence electrons, chlorine is a very active element. Maybe you remember that when we talked about families of elements, right? What family of elements is chlorine in? It's in group 17. What do we call that group 17? Those are the halogens, right? Halogens are very reactive elements. Why? Because they have 7 valence electrons. How many electrons do they need to pick up in order to be stable? Just 1. And that makes them very, very active. They will look for that electron anywhere they can get it. When sodium's around, it's all cool. But when there's another chlorine around, we have a problem. Will this chlorine steal an electron from this chlorine? This chlorine doesn't want an extra electron any more than this chlorine wants an extra electron. It won't take one from the other chlorine. They both want electrons just as much. So, I realize that I'm personifying these atoms and turning them into people that can make rational decisions and stuff like that. But, so instead of one stealing the electron from the other one, they enter into a mutually beneficial arrangement. Say, okay, we both need an extra electron, right? I've got 7, I need 1. You've got 7, you need 1. Let's be fair about this, okay? these two right here, let's share them, right? What's mine is yours, and what's yours is mine. So now, if we take a look at this original chlorine that we drew, right, that has this box around it, these 7 that are inside the box, they, quote-unquote, belong to that original chlorine atom, right? But anything circled in red is being shared. It, quote-unquote, belongs to both of them. So, if we count out valence electrons now, right? 1, 2, 3, 4, 5, 6, 7, plus this one that it's sharing, right? How many has it got now? 8. 1, 2, 3, 4, 5, 6, 7 that it had originally, plus this one that it's sharing now. Guess what? How many does it have? 8. Kevin, go ahead.
Wait, I'm confused. Why wouldn't they just steal one from the other?
Because it's a tug of war, and they're both just as strong as the other one, right? One doesn't have a greater attraction for those electrons than the other one does, especially in this case because they're both chlorine. They both want those electrons just as much. So yeah, like I said, think of it as like a tug of war, and they're exactly as strong as each other, right? One won't steal the other one, but they can share them. Okay? Does that make sense?
Yeah.
All right. So that gets us to the idea behind covalent bonding, where ionic bonding involves the transfer of electrons between atoms. Covalent bonding involves electrons being shared between atoms. So, covalent bonding. Atoms will share valence electrons so that both achieve a stable electron configuration. And we've learned already, right, that a stable electron configuration looks like what? How do we know when something has a stable electron configuration? 8 valence electrons. That's what a stable electron configuration looks like. There is still an attractive force that holds those atoms together. I will show you that attractive force in just a second. But in words, right, it says the attraction between the shared electrons and the nuclei of the individual atoms holds the atoms together. So there still has to be an attractive force. That's what a bond is. When two atoms share a pair of electrons, we call that a single covalent bond. Electrons are always shared in pairs. There is no such thing as a single electron being shared. Atoms will share pairs of electrons. Not one, but groups of 2. Good there? So, if we go back to our original picture, right? Here, this pair of electrons that are being shared, we call that a single covalent bond. In terms of the attraction, this chlorine atom, we drew the Lewis structure because we're only really worried about the valence electrons. But remember, there's a nucleus in here, and that nucleus has a positive charge. It's attracted to things that are negative, like electrons. It's attracted to the electrons that are part of the original chlorine atom, but now it's also attracted to this electron. This chlorine atom has a nucleus that's positively charged, and it's attracted to this electron, right? Technically, right, if we draw that box again, this electron right here belongs to the chlorine atom on the left, When I say belong, right, belong in air quotes, right? But it's also attracted to this nucleus of the one on the right. That's holding these atoms together. Okay? That's what the bond, the covalent bond is, the attraction that holds the atoms together. There are different ways that we can represent this bond. We refer to this as the electron dot model. Starting off, the electron dot model works great because you're familiar with Lewis structures and valence electrons and stuff like that, right? So these two dots in between here represent the two electrons that are being shared between these two atoms. But sometimes that gets pretty messy and gets very convoluted and there's too much going on to draw all the dots. So we will shorthand that bond and turn the formula into a structural formula. Structural formulas use these lines to represent the pair of electrons that are being shared. So, going back to our picture that we drew here, we could represent Cl, draw a line between them, and Cl like this. And then these electrons around the outside where that line is representing the pair of shared electrons. We call this the structural formula. That's messy, but that's what it says. Structural formula. Good there? So the line always represents a pair of shared electrons. All right. Also on that table, right? So you got your electron dot and you got your structural formula. We're going to use those most often. Down here in the bottom left-hand side, they call it the space-filling model. If we approximate those atoms to be spheres, right, we smush those atoms together and make the sides flat to show that they're sort of impinging on each other's space a little bit because they're sharing electrons, right? And then the electron cloud model, when we talked about orbitals and orbital diagrams and stuff like that, we use the electron cloud idea, right? That dark areas represent a high probability of electrons, lighter areas represent less probability. If you look here, it's kind of a little bit hard to see, but, right, it's darker in between these two atoms. Why? Because what are they doing? What's holding them together? They're sharing what? They're sharing electrons. So if electrons are being shared, where do you think they spend a lot of their time? In between those two atoms. And so that space is going to be dark in there. Okay? Good there? All right. We refer to the formula that we just drew as a molecule. By definition, a molecule is an electronically neutral group of atoms held together by one or more covalent bonds. So, two requirements. One, it's got to be electronically neutral. Two, held together by covalent bonds. NaCl is not a molecule because it's got an ionic bond, right? It is electronically neutral, but it's not a covalent bond. Okay? So, what we just drew here is a molecule. No electrons have come in or gone out of this arrangement here. If we counted up all the protons and all the electrons, they would be exactly the same. Electronically neutral. But they are attracted to one another. This molecule we would call Cl2. Why? Because how many atoms are we holding together? 2. And they're both chlorine. Go ahead, Catherine.
So can only halogens have covalent bonds?
No. I'll show you that in just a second. Give me like 2 minutes and we'll go there, okay? But, Catherine, keep that question in mind at the end of class because I'm going to ask you a different question and I want you to answer it based on the question you just asked me. Okay? All right. Here. Okay. Here's a different molecule. This is a molecule called HCl, or hydrogen chloride. It's one hydrogen and one chlorine. Hydrogen only needs 2 electrons to be stable. Remember, it's small. We said that small atoms can be stable with 2. It's got 1 valence electron based on where it is on the periodic table. Chlorine has 7, right? So they share this. Okay? Here's a molecule you're probably familiar with. You ever hear that one before?
H2O.
Right, H2O, okay, right? H is happy with 2 valence electrons. Oxygen needs to pick up how many, though? It needs to pick up 2 electrons, so it's got to share electrons with 2 different atoms, okay? Here's one that you might not know about, but it's definitely one that you've probably heard, or you may have. This is ammonia, right? This is ammonia atom, molecule, okay? Don't mix it with bleach, right? Okay? But in this case here, right, sharing electrons, sharing electrons, sharing electrons, okay? Good there? The molecule that we drew originally is a specific kind of molecule that we call a diatomic molecule. A diatomic molecule, by definition, is a molecule that consists of 2 of the same kind of atoms. So, Catherine, this isn't the question I was going to ask you. I'm going to ask you a different question, okay? If chlorine forms a diatomic molecule, what other elements do you think might form diatomic molecules?
Anything in any halogen.
Any other halogen, right? So that takes us to fluorine, chlorine, bromine, and iodine. Okay? They all form diatomic molecules. Here's what I want you to do next. On your outline, either back on the front page if you want a little bit of space, or you can go to the back of your outline, completely blank. There's a lot of space to draw stuff there. Okay? I want you to draw for me the Lewis structure for oxygen. Draw me the Lewis structure for oxygen. All right, does your Lewis structure for oxygen look like this? Not exactly, but does it have 6 valence electrons?
Yes.
Yes, okay. So, don't write this down, but earlier in this unit, calcium came around, right? And calcium is looking to do what? Lose 2 electrons. Oxygen is looking to do what? Gain 2. It was a match made in heaven, right? But calcium's not around. The only thing that's around now is another oxygen. Okay? So, this oxygen, right? Oh, let's group this. Oh, that's already grouped together. Look at that. This oxygen, right? So, oxygen on the left, it's looking to do what? Gain 2 electrons. Oxygen on the right, gain 2. Does this oxygen want electrons more than this oxygen? No. Neither one of these oxygens will steal electrons from the other one, but they will do what? They will share. So, what's mine is yours and what's yours is mine, right? It shares. Remember, sharing happens in pairs. Okay, so in this case here, it shares a pair of electrons. If we count them up now, right? 1, 2, 3, 4, 5, 6. valence electrons that it had, but here, right, gets you to 7. Is it happy? Is it done yet? No. So, if 1 is good, 2 is better, right? So, here, in this case, oxygen will not just share 1 pair of electrons, it will share 2 pairs of electrons. Is everybody happy here? Okay? Yeah, everybody's happy now, right? This oxygen, hey, chill out over there, okay? Had 6 to begin with. Now it's sharing these 2, right? Everybody's happy. Okay? Next thing I want you to do, just on the back of your paper there, okay? Draw for me, sorry, first, before we do that. Is this a molecule? Yes. Specifically, we would call this a what? A diatomic molecule, because it is a molecule of 2 of the same kind of atoms. This is specifically O2. Okay? Probably heard of that one before, right? All right, next thing I want you to draw for me. Draw for me the structural formula for the diatomic molecule N2. Draw for me the structural formula for the diatomic molecule N2. So start off with a Lewis structure. Based on nitrogen's position on the periodic table, how many valence electrons does it have? 5. All right, so up on the board, there are my 2 Lewis structures. We said both of these nitrogens are looking to gain 3 electrons, but one doesn't want electrons more than the other one. So they won't trade electrons, they will share electrons. These 2 here, these 2 here, and these 2 here. Right? So we said a structural formula does what? What's the change in going from this picture to a structural formula? Trey?
You just replace those 3 circles with a line.
Place those circles with lines. The lines represent shared pairs of electrons, right? So N, 1, 2, 3, to represent each shared pair of electrons, right? And then you got these extra electrons on the side. Is this a diatomic molecule?
Yes.
Yes. Okay? So let's finish up some things on your outline here. Right? First, there are 7 elements out there that will form diatomic molecules. The 4 halogens that we previously talked about: chlorine, chlorine, bromine, and iodine. Oxygen, which we drew. Nitrogen, which we drew. And then also hydrogen. Those 7 are the only elements that we know of that form diatomic molecules. Okay? On the back of your outline, when I had you draw some pictures, I introduced you to the concept of multiple bonds. So multiple bonds, right? Hey, everybody, don't forget we're on homeroom schedule today, so we're something like 5 minutes long.
So I have a quick question. Where do we put those 7 elements
You just
together?
write them next to it. So. Multiple bonds. Some atoms are held together by sharing more than one pair of electrons. When we drew the oxygen molecule, how many pairs of electrons did the oxygen molecule have? 2. Guess what we call that? That's going to be a double bond. Where 2 atoms share 2 pairs of electrons. Any guess what we call the nitrogen?
Triple.
Nitrogen has a triple bond. Where 2 atoms will share 3 pairs of electrons, or a total of 6. So, the next thing that comes up, we've got 2 more things to do. Nothing you have to write down, just things we have to talk about. Okay? But keep your stuff out. You don't have to start packing up. All right. The next thing that comes up is, well, here's carbon. Right? 4 valence electrons. What if another carbon came around? In theory, what could they do here? They could share how many pairs of electrons? 4, right? 1, 2, 3, 4. Okay? Would that get everybody to 8?
Yeah.
Yeah. But this doesn't happen. Okay? We said that if electrons are going to be shared between atoms, where are those electrons going to be most of the time?
In the middle.
In the middle.
And they repel each other.
What's the problem with having 8 electrons in this space?
They're gonna repel.
They all repel each other. This doesn't happen in nature. Looking good.
Would nitrogen be a triple bond then?
Yeah. It's got 3 pairs of electrons, right? Yes, nitrogens are triple bond.
What?
Hey, relax. All right, so 2 things. Catherine, earlier on you asked me a question, and you said, are halogens the only kind of elements that form covalent bonds? And my answer to that question is no. But all of the elements that I have had you guys draw today on the board have all been what kind of elements? Where have they been on the periodic table?
Non-metals.
They're all nonmetals. Hey, hold on. They're all nonmetals. Why? Because what does a covalent bond require?
2 nonmetals.
2 nonmetals, because why? Because they're both looking to do what?
Get rid of
No, they're not looking to get rid of electrons. They're looking to gain electrons, right? You can't share electrons if both of the atoms are looking to give them away, right? So, answer to your question, Catherine. No, halogens aren't the only ones that form covalent bonds, but they have to be nonmetals. More than 4, right? Or actually 4 or above. That's generally what we're saying. Just because carbon forms covalent bonds, just not a quadruple covalent bond. It'll share with other things, but just not with itself. Okay?